This talk is about flavors of Postgres. We're going to be talking about some of the more recent open and closed source iterations and extensions of Postgres, and how you, a database implementer, a data chef, might want to choose one of those. So on today's menu, we're going to talk a little bit about me very, very briefly. We're going to talk about deriving things from Postgres, things that are compatible with Postgres, things that are extended from Postgres, and what the difference between those different types of relationships with open source Postgres are. We're going to talk about why forking matters and realistically, like why being open source matters. And then we're going to have a few closing remarks. I'm going to try and leave time for Q&A, but realistically, like it's not looking good, guys. But I'll totally be around after. So your host with the most, my name is Celeste. Up until like 2 weeks ago, I was a developer educator at Ivan, and now I am currently accepting freelance technical writing clients and/or full-time opportunities. I was unfortunately hit with like a restructuring. As a result, you're going to see this lovely QR code in the upper right. That just goes to my LinkedIn profile. I would love to connect with you, and I'm definitely looking for my next opportunity. I would describe myself as an open source true believer. Some of my past work experience includes time with the Linux Foundation, working directly on the Kubernetes project as a technical writer. And since that point in time, I've really tried to work in open source aligned companies and with open source aligned opportunities. I'm a technical writer by trade, but I do love giving talks and just like love kind of educating and communicating with people. And this is me here at a restaurant here in Berlin, as captured by my friend a couple weeks ago. The cool thing about being unemployed, and there are not a lot of cool things about being unemployed, just to be clear, is that I no longer have a company-backed horse in this race or in this presentation, which was not true when I first proposed it 3 or 4 months ago for submission. And as a result, I can give you a fairly unfiltered opinion as to what I really think and feel about some of these databases. A lot of this is going to come from a presentation that I gave to Ivan's kind of clients and prospects back in March. But the things that are all me and that are kind of my opinion that is unhindered by anybody else, you're going to see in green. The rest of the slides are going to be kind of in red, okay? I apologize to anybody who's red-green colorblind, by the way. I just thought about that right now. Okay. Before we kind of dive into it, I think it's really important that we review what makes Postgres Postgres-y. And I think a lot of these are things that are super obvious now in 2025. But back in like 1990, when Postgres was first coming into its own as an open source project, these were all a pretty revolutionary set of principles and ideas in regards to software design in general, but also databases in specific. Postgres is super ACID compliant. Database transactions they are atomic, they are consistent, they are isolated, and they're durable. This is table stakes nowadays, but that was not the case 30 or 40 years ago. Data in Postgres is typed. So data must have a type. You can't just have like a whatever in there. Another really big part of the Postgres project when it was first launched was SQL standardization. Postgres adheres very, very closely to the SQL standard, maybe more closely than like almost any other project or database. Relational, again, this is obvious now. This was not obvious 30 or 40 years ago. And the last 2 points are really what we're concerned with today for today's presentation. Postgres is extremely lightweight and unopinionated in its kind of core unextended form. The extensions framework was and always has been a first-class citizen of the Postgres project. Extensions were a part of like the first version of Postgres, more or less, and have continued up until today. And this extensibility is what has kept Postgres relevant all the way until 2025, and it will keep Postgres relevant in the future. That and the fact that being open source, it is forkable. These two things really contribute to a very vibrant community of technology around this database that, again, keeps it relevant and keeps it from kind of going stale. So, super duper duper high level overview of how Postgres works, and this is important because we're going to compare and contrast architecture diagrams as we go through. So, you can kind of think of Postgres as working in like 3.5 to 4 layers of functionality. We have the client processes over here on the left. This is where a client application goes, hey, can I connect to your database, please? Those client processes then kind of communicate with a bunch of background processes that handle the inner workings of Postgres. Probably the most important is the write-ahead log, which keeps, as you might assume, a log of things that it intends to write in the database. And this allows you to kind of do rollbacks a lot more easily than you could in other models. There's a bunch of other stuff. The auto vacuum is maybe the other interesting piece because it's a bit of garbage collection and it is pretty smart. We're not going to go into too much detail. Those background processes communicate directly with a bunch of system memory that is chunked aside for different things going on in Postgres. And it's from that system memory that things are then written to file storage. That's all we need to know for now. There's way more you can say about this. So before we move on, let's also kind of establish what do we mean by flavors. There are different ways that somebody can augment Postgres. The biggest and most common in a lot of ways is things that are directly forked from Postgres. We're going to go through a couple of those today. These are either open source or under BSL licensing, and they either augment or modify Postgres's core functionality. There are a lot of businesses that make a lot of money that are built around forks. The next, and probably the most interesting and the most sort of vibrant parts of this community are extended directly from Postgres, so they work with Postgres extensions framework. PostGIS, Timescale, pgvector all fall into this category. And I just want to call out PostGIS in specific because I think people don't realize how important that project is. It basically powers all of open map data, which powers every map-based application that isn't like Google Maps for the most part. It's a really foundational part of modern life. And it's totally open source. It always has been, and it's a Postgres extension, which is pretty cool. These install to any Postgres instance to which you have access to the create extension function, and a lot less relevant to us are patches and add-ons. Now let's talk about this asterisk points, which is showing up real light on the projector. Here's my first caveat. My biggest thing that I would say to you is there are not a lot of database administrators out there in the world these days compared to how things were maybe 15 or 20 years ago. And there are a lot more managed database providers of various sorts. The major cloud providers are one of them. My former company, IBM, was another. A really important thing to note as you're moving through your technology journey with Postgres as a database is that a lot of managed service providers don't grant like carte blanche access to adding extensions to Postgres. So if you're going the managed service provider route, you might not have access to the wonderful world of a lot of these extensions. And they are a really important part of this ecosystem. So let's talk about the various flavors of Postgres we're going to talk about today. We're going to talk about AlloyDB Omni, which is Google's closed source AI optimized reimplementation of Postgres. And we're going to talk about kind of how that works. We're going to talk about Amazon Aurora and Neon, which are very, very ideal, like from an ideas perspective, very closely related. These are both serverless implementations of databases. Neon is very specifically a serverless implementation of Postgres. And then we're going to talk a bit about sort of open source Postgres 17. We're going to talk about some like really exciting things happening in the ecosystem today, and like why that's important. So let's dive in. Let's talk about AlloyDB Omni. So what it is, and direct quote from kind of their documentation, it is a fully managed Postgres-compatible, this is a phrase you're going to see a lot today, database for demanding transactional workloads, yada, yada, yada. Postgres compatibility is an interesting thing because Postgres is one of the most widely adopted databases out there. There is a lot of money in producing something that is Postgres compatible, but all of the companies that we're going to talk about today that are kind of producing closed source for-profit things claiming compatibility mean different things when they say the word compatible. I read through AlloyDB's documentation up and down like twice preparing this presentation. And I could not figure out what Google Cloud means by compatible. They just say it's compatible. We're going to contrast that with AWS Aurora going forward and with Neon, and you'll see that there are very different ways of defining compatibility. What I have figured out just by sort of reading through the documentation is that this is more or less a fork of Postgres. They have added some functionality to implement specifically AI and ML workloads, as well as a kind of lightweight columnar database engine. And they've rewritten a lot of the background processes to be optimized for kind of management within the cloud. As far as I can tell, and we're going to talk about that too, AlloyDB Omni is like, ooh, temperature warning. Direct from the cloud providers. There are services like my former employer, Ivan, which will allow you to deploy the Omni version multi-cloud. Let's see if my laptop survived, y'all. And via Docker as a container image. And we will talk about that Docker container image. So, revisiting our Postgres diagram, remember these layers. And then let's look at the architecture diagram from the Google Cloud documentation. And you'll notice that we have roughly the same layers. The biggest difference in terms of that like little slice of pie is that we have separated storage from compute. So the storage lives directly in the VM, and AlloyDB lives inside a container. And that's a thing that we're going to see a lot of today is the separation of storage and compute. It's a very, very common like cloud computing paradigm. You'll also notice these ones highlighted in purple. This is what they're calling their AlloyDB components. The net new are obviously the columnar engine and the AlloyDB AI and ML worker. But you'll notice that they have effectively augmented and refined the auto vacuum. They've added some additional functionality to the write-ahead log, pretty much to manage the columnar engine stuff. And they have optimized memory management in the cloud. But this is extremely Postgres-shaped. And that's a pretty good thing, actually, because it means that you're not really going to struggle with compatibility issues. Here's my major caveat. AlloyDB's documentation is not great. In fact, I would kind of sort of say it's, especially as somebody who has worked on documentation professionally, like pretty bad and extremely light on the ground. So this is basically the only view that we have of what AlloyDB actually is. It's hard to find more detail than this diagram. To me, that's a really big problem because it means that you as a development team cannot be self-sufficient in this piece of technology because who knows how it works. And the Docker container provided, if you decide to go the AlloyDB Omni route and deploy it yourselves, is a black box of a Docker container. Like, you can really have no idea what's going on there. And I don't love that, especially to recommend to a potential client. But let's talk about the positives. AlloyDB provides additional vector support, so they effectively have a kind of additional extension to pgvector, which they just call vector. It adds some additional indexes. If you have a reason to need to access additional indexes, look into it. I don't actually think you have to use it with AlloyDB Omni. I think you can use that vector extension with any Postgres database, but they sort of kind of pretend like you can only use it with AlloyDB Omni. The main like sell, in my opinion, is it allows you to query models remotely from Google's Vertex AI Garden. And these are obviously going to be super high quality models and super reliable. And you can do that all basically directly from SQL, as opposed to sort of having to like involve a scripting language. So if that's a way that you want to work, this is like a really, really compelling way to go about it. The other major thing that we touched on is the columnar engine. So without going to columnar databases, basically at some point with a certain amount of data, it becomes more effective to look down a column than to look across at rows. And most relational databases by default are looking across at rows when they're doing like a select. So this allows you to do some like very lightweight columnar activity without having to commit to something like ClickHouse, which is like a really major technical decision. So it's a kind of nice little feature to have, especially if you're doing a lot of analytics or if you're churning a lot of data for those sort of AI and ML workloads. I will call out it's not a columnar database. It's fundamentally transactional. It is fundamentally Postgres under the hood, in my opinion. So this is the slide I would give you if I still worked at my last company. Here is my more unfiltered opinion that we're just going to slap over it. I would recommend AlloyDB to anybody who is already on Google Cloud, quite frankly, because the big juicy features are going to be Google Cloud features anyways. I would recommend it if you're kind of non-committal about AI and ML, but you need a little bit more than PT vector. I would also recommend it to anybody who is looking to experiment with whether accessing data using a columnar engine is right for you and your data set in your business, because this is again, a slightly less committal way of trying out a ClickHouse type model without having to invest in a full database migration, which is usually a hot mess. I would also recommend it to anybody who wants to kind of try one of these next-gen databases but still values portability of data, because this is the most architecturally similar to core Postgres. So you're probably going to have less problems extracting data if you do want to leave. And why you might not want to. Like I mentioned, the documentation's not great. You're just not going to be able to become self-sufficient as a team in this, and I think that is a really, really important thing to do. I feel like you'd always be going back and forth with Google support. The Docker container, also a black box. You have no idea. A lot of the documentation they provide is also for AlloyDB on Google Cloud, which is not the same as AlloyDB Omni. And so it's really hard to tell if some of the things they recommend for AlloyDB on Google Cloud will work in the same way on AlloyDB Omni, because there's just no telling. And finally, the AlloyDB Omni edge compute story is basically the Google Cloud edge compute story, which is definitely a pretty good edge compute story, quite frankly. But as we'll see with AWS Aurora and Neon, if edge computing and sort of serving data really, really fast in different availability zones is a high priority for you, frankly, I think there's better options. Okay, speaking of that, let's talk about AWS Aurora and Neon, and we're going to talk about why we're grouping those two things together. AWS Aurora, you've probably heard of it. It is Amazon's distributed relational database service. They offer a bunch of different flavors of that, quite frankly, within the AWS service, and we'll talk about that a little bit. Amazon promises what it calls end result compatibility with Postgres. And so what they mean by that, if you kind of dig into their documentation, is if you had a Postgres database with a table in it, say customers, and you had an AWS Aurora for PostgreSQL database with a table called customers, and you ran the same SQL command against both of those databases, you will get the same result. That does not mean that, from a sort of memory and storage perspective, that those databases are structured or work in the same way. It doesn't mean that you can migrate easily from one to the other. It means that if you query the database, you're going to get the same result. And that's all they promise. Obviously super duper proprietary, obviously only on AWS at this time. This is a super caveat slide differentiating the very different Aurora Postgres-shaped services that they are. I'm not going to go into it in too much detail. If you really want to, I'd read that blog post because it does a way better job than I can. Long story short, they have a bunch of different Postgres-related or compatible things, and I personally wouldn't know how to recommend you one versus the other. And I think this is, quite frankly, a weakness of the Amazon product offering because it's confusing. Simple as that. Brief discussion of AWS architecturally. You'll notice that this kind of just looks like a high availability service, and it could kind of sort of be any service that stores to an S3 bucket. And that's roughly the caveat, is the Amazon documentation is very, very thorough, but they don't necessarily go into the architecture details of the Postgres specific services. So broadly speaking, it's that. It's perhaps a little bit more informative to look at the DSQL version of Amazon Aurora, and we'll talk about why in a couple of slides. But for now, memorize this part. Basically, the application is going to hit an endpoint. The endpoint is going to talk to a bunch of different availability zones, which are going to spin up and spin down read and write surfaces based on demand. Those availability zones are all writing to transaction logs on their own little column. And they're ensuring consistency between those transaction logs, and the transaction logs are talking to the storage layers. And that's more or less it. Again, things spin up or spin down based on the demand in the availability zone, and that's all handled like magically in here. Let's briefly talk about Neon. What is it? It is a serverless distributed PostgreSQL. I think the cool thing about it is you can interact with it using pSQL or other Postgres-related tools, no problem. Very specifically, and they called this out in their marketing and documentation, it's based on the Amazon Aurora white paper. There are two big stars around Apache and direct through Neon, and the reason is that like 2 weeks ago, Neon got acquired by Databricks, so like who knows what's going on now? Great for the people at Neon, though. Okay. This is the Neon architecture diagram from their documentation, and you may notice something similar from a couple of slides ago. We have a compute layer. The application would be over here. It would hit that layer. These are spinning up and down based on availability. They're writing to a safekeeper, or you might say a transaction log, which is then talking with the background services, and the object storage is kind of over there. And of course, to bring back our sort of Postgres diagram, you will also realize that this kind of sort of looks nothing like Postgres. And that is a really, really important thing to note when you think about both Neon and AWS Aurora. The big idea that both of them are driving at, and quite frankly, Google with AlloyDB is also driving at as well, is decoupling storage from compute. I highly recommend, if you're interested in this, researching or looking into the Amazon Aurora white paper. It is really fascinating reading. But just to kind of pull out some ideas, when you look at the world from a cloud-native perspective, basically you are looking at the idea that a service will fail, full stop. It will always fail. It will fail at some point. It's just a matter of when. This is really problematic when it comes to data storage, because you ideally do not want your data storage to fail, because you want your data to like still be there. And this is why databases have been difficult to run in the cloud up until this point. Per the white paper, instance lifetime does not correlate well with storage, which is a very polite way of saying the compute layers can and maybe should die all the time, but ideally we do not want the storage layer to die. So really, everything that we've covered up until this point is trying to get away from the tight coupling that sort of open source Postgres has between the compute processes and the storage. However, as a result, and particularly in the case of both Amazon Aurora and Neon, the reason that they're offering this sort of like end result compatibility is because to get to this real separation of storage and compute and get to this place where you can be available in multiple availability zones, you have to create something that is so fundamentally not Postgres shaped that you can't offer like true compatibility, right? And that's like, this is where I would normally rag on serverless for a bit, because my last company didn't have a serverless offering, but but I don't work there anymore. So why you might want to use AWS Aurora or Neon, I think these are like pretty much the cutting edge ideas in like data storage these days, in my opinion. If you are serving a truly global audience, you need that data available in different availability zones at the edge. Then I think you have to go with an edge computing solution. And quite frankly, if you're doing a true edge computing solution, you're probably already vendor locked in anyways, so like you don't really care. You're comfortable with the relative data lock-in. This is a really, really big one. They don't really have documentation for migrating off of these services, so like I kind of think you're SOL there. Reliability without sacrificing read speed is a really, really big one for edge computing in general. And I would say the other one, and I apologize for the lack of contrast on this, geez, you've got a dedicated DevOps and SRE team. I don't think you can accomplish this without. And I think that Aurora specifically is more of a cloud computing thing to understand than it is a database thing to understand. But why not? I think if you want more handheld support, you're going to end up with AWS. You're going to be a small fish in a big sea. I think if you have other means of sort of storing data for portability purposes, I think if you care about data portability, this is maybe not the solution for you. And quite frankly, the example I always use for this is my bank, N26. My mom lives in the Philippines. When I went to the Philippines, accessing this bank was horrifically slow because they don't need edge computing. Most of their clients and customers are staying within Europe, so why would they spend the time and the energy making the application efficient in Southeast Asia? I think you just really need to evaluate whether your business actually has this need. But enough about that. Let's talk about Postgres. So we're going to touch on this briefly later in the talk, but the Postgres community is alive and well. They're producing really, really, really interesting features. Here are exactly 2 of them from Postgres 17, and there is way more in that release. I would say that the most interesting feature, one, is incremental backups. This was introduced again in Postgres 17. It introduces this idea of the while summarizer background process, which lets you take incremental backups in addition to full backups, which drastically reduces the amount of compute required to take a backup, which is a very, very good thing. Here's some detail about how you would do it. Don't worry about it. Again, this is a huge efficiency win, and backing up databases is, in my opinion, way more important than serving data in some ways. So that's number 1. Sorry, we're kind of zooming here. This is number 2. JSON tables. This is actually a really, really big one. So Postgres implements the SQL to JSON data model, which allows for transformations from JSON to a database table and back and forth. This is super, super important if you ever read data from an API, which I assume you probably have in your careers, because most APIs will send you data as JSON, or they have an option to send you data as JSON because it is so, 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 so common. And this allows you to natively do the transform on that data within SQL and within Postgres, as opposed to having to decode that JSON and drop it into Postgres elsewhere. So it's a lovely little time-saving thing. Let's talk a little bit about extensions. Again, super, super briefly, because I'm kind of running up at time. There's a lot of fascinating things happening in the extensions ecosystem, and I cannot do justice to them with 3 slides in this presentation. The first slide I want to talk about is Timescale. Timescale is a super cool company full of super cool people with incredibly complicated product naming. So their Apache edition is their open source version of Timescale DB. They have a community edition, which is not open source or community based. It is, in fact, an enterprise edition. But the main thing that Timescale DB does for you is it allows you to use this idea of a hypertable. It allows you to use this idea of yeah, I'm with you, dude. It's goofy. They allow you to use hypertables. A hypertable is basically a table that's been kind of indexed by time. And what it will effectively do is kind of create sub-tables within that table. So if you're doing, say, a query for analytics purposes and you know a particular timestamp that you're interested in, you can access that data a lot more efficiently and perform actions against those subsets of data a lot more efficiently. It's a great extension to Postgres, especially if you're doing any kind of analytics. It really, really speeds things up. And again, it's made possible because Postgres has this really robust extensions ecosystem and this permissive licensing. Another one that I want to talk about is a project called Cloud Native PG. So this actually isn't really an extension. This is a separate project. It's licensed under the Cloud Native Computing Foundation, and it comes out of Enterprise DB. It is a very fully featured Kubernetes operator for a highly available Postgres cluster. As we mentioned, managing Postgres in the cloud is a bit of a nightmare because of the tight coupling of storage and compute. But the other reason is it's just a technology that existed before the paradigm of cloud computing existed, so it's a little mentally incompatible. I kind of feel like the killer feature of Cloud Native PG is that it allows basically anyone to manage a Postgres database using Kubernetes. And this seems really trivial, but this was not actually available before this project. For example, my last employer, Ivan, had a Kubernetes operator for its Postgres services, which were in a cloud, but only for Ivan services. And that's actually a pretty common pattern. So it's a pretty big win to have this available for the community. It's under the CNCF, so it's going to continue to be open source forever. And again, I think that's a huge win. It's Postgres. You're not going to have any compatibility issues. You got an SRE team, go nuts. And the last one that I want to talk about, this is actually out of Microsoft, and I believe it is, I don't know if it's under the CNCF or under the LF. I think it's just like on their own. It's called DocumentDB, and this is an extension to Postgres, and it provides document data storage, so like a MongoDB-like solution. It's not really a MongoDB clone. We're not going to get into the details of that just now. If you did want a MongoDB clone, I would actually recommend the FerretDB team. They're lovely people, and they're actually trying to build more of an open source MongoDB clone. But it's available for you if you want to try that out. So why vanilla Postgres right now? Maximum forward compatibility. You're never going to have like Postgres compatibility issues or going to and from Postgres. You're going to be fine. It's Postgres. You're going to get the full power of the Postgres extensions ecosystem, full control, and there's a really robust community of service providers and architects and managed services and companies that specialize in Postgres that has developed over 30 years. Like any resource you could possibly want, you will find. But also potentially, why not? Not everybody has the headcount for like a dedicated database person, and that's like legit. A lot of people are trying to hit committed cloud spend in a specific cloud, and like that's legit. Like go spend your cloud on a database. The other thing is, if you're like super duper duper heavily invested into AI or analytics or edge computing cases, like there are really specialized solutions for that, and you should definitely consider those. We're making our way to the end of the talk, though. I just want to shout this out, which is when I started writing this talk, I found these slides from Josh Burkus, who is a friend of mine from Kubernetes stuff. Though this was long before his time in Kubernetes, this was in 2009, which covers a lot of the same topics, but like 15 years in the past. And I just think that's like such a fun feature of the Postgres project and the Postgres community is that it has always been forked. It has always been extended. And because of that, there are businesses that can be sustained on it, and the project itself can be sustained in turn. To err is human, and to fork is Postgres. Like I said, forking keeps the community strong. If we sort of look at the core team of Postgres committers, you'll notice that they're driving ecosystem expansion. Cloud Native PG comes out of EDB. DocumentDB comes out of Microsoft. They're driving service and support, LinPro, for example, but honestly, all of these companies are providing that. And they're providing a lot of innovation. It's the forking that allows this to happen, or else projects die. And because I, again, no longer have a paid horse in this race, this is going to be my biggest personal opinion. This is the hot tea. You heard it here, folks. My biggest issue, though, especially with the databases that we covered in the beginning of this presentation, is there's a lot of innovation happening to enable data storage in the cloud and to enable data processing in the cloud. But because those are closed source, and because they're proprietary to cloud advisors, those concepts, though they are universal, that idea of storage and compute shows up in all three of them, right? They aren't making their way back to open source Postgres. And that's going to be net detrimental to Postgres as a project, but also development as a whole. Because those ideas are going to stay locked up in those cloud providers, and they won't pollinate and germinate the next generation of innovations, because that's what happens when you open source things. So there's a lot of cool stuff, and I really question the distribution methods. And that's it. Talk to me about freelance, full-time, or technical writing, DevRel, especially if you found this was a cool or helpful presentation. Thank you so much for your time. And we have about 5 minutes if you want to take some questions. You need to wait for the mic because they're streaming it. That sounds like it's on now.
All right. So again, thank you for your talk. I wanted to ask about On one hand, about the document DB. So on one hand, we have something on top of, something that extends PostgreSQL with document database, let's say, capabilities. On the other hand, we have this growing support for JSON in PostgreSQL, and this feels like a convergence, right? Because if you look at MongoDB, for example, at least the external representation of documents is JSON, right? So is this something that would converge, or is it something completely different, actually?
That's a great question. No. So the JSON table functionality, and I apologize for going through it so quickly in the presentation, basically is using JSON to describe a table or to describe data within a row of a table that you want to like insert or update or whatever. Document databases, however, are the primary feature of a document database is that it's kind of just like a key and a value, for lack of a better word. Like it's not like Redis or anything, but like basically you have like an identifier and then you just have like a blob of string data and like YOLO. And they're very, very fast, but like they also kind of cause problems. So same technology, but like very different things conceptually, I think.
Celeste, thank you very much. Give a big applause to Celeste.
Thank you.